Hello AP Physics 1 students, please have your notes open, and in your notes, if this were a normal day, and as I do now, I'd have you write this chart in your notes and then fill it in. So go ahead and start copying this chart down. The first column here is type of field, and the second column is what creates it, and the third column says what used to test for, and here you might be a little confused with what that means, but do your best. I want you to copy the chart into your notes, fill in as much as you can, and then come back and we'll talk about it. Okay, so here we are comparing the three different types of fields we've seen throughout the year. We'll start with gravitational fields. First, to remind ourselves, what's the symbol for gravitational field? Right? Not gravitational force. Force is always F. There's gravitational field, and of course it's a lowercase g. Remember, capital G is the gravitational constant. There's no physical meaning to that, but gravitational field is also acceleration due to gravity. All right, so what creates a gravitational field? Well, hopefully you wrote down not just Earth or, something like that. It should be mass. Every mass creates its own gravitational field. Of course the Earth does, but so does the Moon, so does the Sun, so do you. Create your own gravitational field. Any mass does. Okay, how about this third column? Well, let's imagine you're an astrophysicist, and it's your job to map out a gravitational field in some location in space. The question is, what would you put there that would test for it? What would respond to a gravitational field? Okay, so what responds? It's going to be another mass, right? Any other mass will respond to the original mass's gravitational field. In fact, what's happening is that this mass is interacting with this one's gravitational field, and this one's interacting with this gravitational field. They're interacting with each other, and that's the gravitational force, gm1m2 over r squared. Okay, what's the symbol for electric field? Hopefully remember that's a capital E. Okay, what creates an electric field? Hopefully you didn't just say charge. You should say it's any object with net charge, and that's how we wrote it the first time, back when we first compared gravitational force to electrostatic force. Right? And it's not just protons and electrons, it's like balloons, right? If you take a balloon, rub it on your hair, you give it a net charge, it creates its own electric field. So, let's say you're in a lab and it's your job to map out the electric field in some location in the lab. What could you put there to test for it? Well, we know what the ideal is, the positive test charge, but remember, it doesn't have to be positive test charge. It's really another object with net charge. Yes, it's great if you got positive charges, but what if you have negative charges? They'll still respond to an electric field. What if all you have is a bunch of balloons? Take the balloons, rub on your hair, put them there, and they will respond to the electric field. So really, any other object with a net charge. What's really happening is this charge is interacting with the field produced by this one, and the interaction is the electrostatic force. If they both act as point charges, that's K, Q1, Q2 over R squared, right? Each one creates its own field, the other one responds to that field. That's the force. Okay. What's the symbol for magnetic field? We learned in last class, of course, that's capital B. Now, what does capital B really stand for? You might remember. Oh yes, magnetic flux density, but we don't really call it that. Okay, so what creates a magnetic field? Don't overthink this one. Hopefully you wrote down a magnet. Of course, a magnet creates a magnetic field, of course, right? Alright, so let's say you're in the lab, and it's your job to test for the strength and location, direction of magnetic field. What would you put there to test for it? I wonder. Ah, yes, of course. It's another magnet. That's the idea, right? Whatever it is that's creating the field is also what responds to it. So you put another magnet there, it'll respond to the field produced by the first one, they'll apply forces to each other. But we also saw, by watching the video last class, that there are other things that respond to magnetic fields. In the oscilloscope, there was no magnet there. You put a magnet outside it, right? The magnet created a field, and the things inside responded. Those things inside were moving electrons. And so we see that moving charges also respond to magnetic fields. They feel magnetic forces in the presence of a magnetic field produced by a magnet. Excellent. Okay. Let's turn to our problem set, and we're going to start here with problem number 4. So just in case you're a little confused, these cylinder-looking things are really just wires that have currents inside of them. Each wire is the same length L, and there's a uniform magnetic field, in this case pointing to the right, denoted here by capital B, and these vectors near it. And the wire is just a different orientation, and we're going to figure out the magnetic force. So the question is, since we have two different equations for magnetic force, which equation to use? Is it QVB sine theta or ILB sine theta? Pause the video, write down which one you think it is. Okay, so hopefully you chose ILB sine theta. As I was trying to tell you last class, the equations kind of tell you what to do, right? QVB sine theta has Q, which is the charge on a moving point charge, and there's no point charges here. ILB sine theta has capital I, which is the current. And so if you see a wire with current, clearly it's going to be this equation. And I know it's very obvious right now, but in future problems, when we have maybe a mixture of moving point charges and wires with current, you better be able to choose which one is which. If you ever find yourself sort of making up a current or making up a point charge, chances are you have the wrong equation. Okay, so at this point, it's just a matter of plug and chug. Go ahead and find the magnitudes of all the forces, and then if you feel confident doing the right-hand rule, go ahead and try that, but I will lead you through it to remind you how it works. Okay, so for the first one, here's the current, Here's the length of the wire. Here's the external magnetic field. It's a 90-degree angle, as shown here, but also shown here. And we should be getting 0.016 newtons, and the force should be into the page. So how does that work? Well, remember, we do our right-hand rule with our pointer finger pointing the direction of motion of positive charges, and conventional current follows the flow of positive charges. So our pointer finger is pointing to the top of the page. Remember, we're not going to use the words up and down. If you're still thinking about up and down, you got to get that, that verbiage out of your vocabulary. We're not going to say up or down because my up is not the same thing as your up. You're sure it's up on the screen, but on your paper, up, the charge is moving to the top of the page or away from you. So we're going to say top of the page. So our pointer finger is pointing to the top of the page. Then we twist our wrist so we can comfortably curl our fingers to the right. The magnetic field is pointing to the right. And you should see your thumb is pointing into the page. We show into the page with the X. That's the tail of the arrow. The circle here is the optional part, but the X is the important part. For letter B, all we do is change the angle. We get 0.011 newtons, and now the charge is moving to the top right corner of your page. The field is still to the right, and so your thumb is still pointing into the page. We change the angle to 30 degrees. We're getting 0.008 newtons, but again, our thumb is pointing into the page. We do the right-hand rule, and lastly, we should be getting 0 newtons. Why is it 0 newtons? Well, there's a bunch of ways to think about it. One is that the angle is 0, so sine of 0 is 0, but if we try to do the right-hand rule, the charges are moving to the right. The field is also to the right. When you do that, there's no preferred direction for your wrist to rotate, and so there's no way to even curl your fingers, and that's what's necessary. We know that charges have to somehow cut across field lines to feel magnetic forces. If the charges move with the field or directly against the field, they feel no magnetic force at all. So it's going to be 0 newtons. Okay, so now I want you to turn back to your notes page where we had first looked at the fundamentals of magnetism, and on the back we have a picture of a bar magnet, and now we're going to start to look at more of a qualitative view of magnetic fields, some pictures of magnetic fields and ways to visualize them. You're going to watch a video that shows that.